慧文，你这个还是不行啊！你这个我还是要只能用手机端登录，电脑端登录不了。
要不我这也行，如果需要的话。
我看我来说吧，反正就手机端登录。那个高宽到了是吧？
是曲老师，我在。
好，那我们开始。因为那个主办方要求用英文哈，接下来我用英文来主持。Hello everyone. It is such a great honor to moderate this series. In 2024, last year, together with Jonas Eliasson of Sweden, Max Shen of Hong Kong, and Juan de Dois Otuza of Chile, Kevin and myself, we organized a special issue of next generation smart transportation systems with the Journal of Frontiers of Engineering Management. So we finally collected 10 papers from multiple countries. So today we will have 3 speakers who are also our special issue authors talking in a few minutes a range of topics from EV charging, activity travel chains, and autonomous driving. So our first speaker is Associate Professor Kun Gao, who was my former colleague, and we almost worked together for the entirety of my 4 years employment in Sweden, and we have jointly published, I think, over 20 papers, during over the past 5-6 years. And today, what's your topic? Today, the topic is regarding EV charging, right? And Dr. Gao, the floor is yours. You have roughly around 20 to 25 minutes for your presentation, and followed by a few questions and answers.
Okay. Thank you so much, Professor Chu. And I'm going to share my screen. No, it's not the right one. Sorry.
No hurry. Take your time.
Yeah. Thank you, Professor Chu. I hope you can see my screen now.
Yes, we can.
Yeah. Thank you so much, Professor Chu, for the introduction, and it's a great honor to be here to share some research we have done about transportation electrification. And it's very nice to meet Professor Chu again online. As mentioned by Professor Chu, he guided me a lot when he was in Sweden and working at Chalmers. So, as mentioned by Professor Chu, I'm Kun Gao, and now I'm working in the Department of Architecture and Civil Engineering at Chalmers University of Technology in Sweden. And today, the presentation I would like to share is about integrated optimization of charging infrastructure, electric bus scheduling, and the energy system. So I will share 2 connected research in the same topic, and the research was done by myself and also my colleague Aslan Xiaohe and Hong Kong, as I list here. So now let us get into the general background. I think it's widely known that transportation electrification is an ongoing trend and is being promoted by almost all the countries around the world, especially in China and in Europe, because of the benefit of the electrification to reduce the emission and also improve the energy efficiency. But for USA, we never know. You never know with Trump, right? So as we all know, that transportation electrification has very much benefits, but at the same time, it's also introduced challenges to the transportation system. So for the public transit, so we need to provide the charging infrastructure and energy supply to charge the bus if we like to change the traditional bus into electric. At the same time, because of the charging needs, so the charging time is commonly longer than the refuel time if you compare to refuel at the gas station in the conventional bus. So because of the charging time, we need to re-optimize the operation scheduling of the bus system to accommodate the charging needs. Another need is that the electricity supply to the electric bus, if we would like to change, a very large percentage of bus to be electric, and also the potential impacts because of the additional charging demand, electricity demand from the electric bus. So the last issue might be more significant in some old cities, especially in Europe. In a lot of old cities, the power system was planned in long time ago, and in that time, the additional electricity usage demand was not really considered in the capacity planning of the power system, like power distribution network. So for this research, we are trying to develop an approach to integrate the electric bus scheduling, charging infrastructure provision with consideration of the energy supply and the constraints from the existing power distribution network. And to satisfy the energy supply, we propose to integrate the renewable energy as a supplementary resource to complement potential shortage in the energy supply from the existing power system. So the objective of the research, we are trying to do the joint planning of the charging infrastructure and also optimize the charging scheduling of the electric bus, considering the constraints from the power distribution network. At the same time, we integrate the renewable energy photovoltaic with battery storage to complement the energy supply to reduce the potential negative impacts of the additional charging demand from electric bus on the power distribution network. To solve the problem, we use Bender's decomposition methods to do the linearization and also reduce the computation burden so we can solve the optimization problem. So what we are trying to optimize, so as shown by the left figure, so we have the electric bus, and we have the station and the depot where we can install the charging infrastructure, and we have the timetable of the bus system that we need to satisfy. At the same time, we consider the power distribution network. So the power distribution network is coupled with the charging point at each charging station. So if the bus is charged at one point, and then it will add the demand to the power distribution, and it will affect the status of the power distribution network. So what we are trying to optimize is the required number of buses to support the timetable of the bus system, and the charging scheduling optimization to satisfy the trips for the timetable, and the required minimal number of chargers to support the charging needs from the electric bus system, and also the energy supply to satisfy the charging demand in the charging point with renewable energy. So as I mentioned before, there is a potential issue in some vulnerable nodes of power distribution network. So we propose to integrate renewable energy, photovoltaic with battery storage to complement potential shortage of energy supply from the power distribution network. So this is our optimization model framework. So in the objective function, we considering the infrastructure cost, including the cost to buy the electric bus, and the cost of installing charger, and also the cost of installing the renewable energy with battery storage. For the operating cost, we're considering the cost of buying electricity to satisfy the charging demand. And to solve the problem, we use bundle decomposition methods. So basically, we divide the problem into the master problem and the sub problem. And the master problem is the operational optimization about when and where, how the bus should be charged. And the sub problem is the infrastructure optimization in terms of where and how much infrastructure you should put in each charging point. So we take a case study in one small city, Hovot, in Sweden, and we get the three bus routes in the city and the timetable. And for the power distribution network, it is really hard to get the real power distribution network because it's a little bit confidential. It is related to the security issue. So we use a IEEE standard power distribution network for the research purpose, as you can see here. So for the three routes, we have 833 trips that we need to satisfy. And because we consider the renewable energy photovoltaic as a potential complementary energy supply source, so we estimate the electricity can be generated by PV based on the solar radiation data from Sweden. And when we optimize the operation and to reduce the operation cost in terms of the electricity cost, we also consider the time of use price of electricity as shown by the red curve here. And we also consider the electricity demand from other sectors because the electricity demand on the power distribution network is not only from the transport, but also from the industrial and the industrial and residential sectors, and etc. So we take the historical data from Sweden for this city, as shown by the blue curve here. This is the electricity demand on power distribution network from other sectors except the transport. So we also consider this. So after optimization, and the outcome will be the first output will be the charging scheduling for each bus. So for example, here the left top figure shows that two bus, how the bus is discharged and charged. For example, as shown by the red curve. So the bus run 2 trips and then charged. So the example, the bus 2 was running for the trip in route 2, but after this trip, the bus 2 run the trip for route 3. So that is more about operation optimization results. So the left bottom figure shows the SOC and energy when the bus finish the trips in 1 day and get back to depot. And the red bar shows the green bar shows the SOC when the bus arrived at the depot after all the trips of that day. And the red bar shows the energy received, the charged energy received at the depot for each bus. So this two figures shows how the energy supply to satisfy the charging demand for the electric bus. So the left figure shows the charging demand from the electric bus in the 24 hours of the day, and the below figure shows the energy supply from the battery storage. So the battery storage can receive the energy from the renewable energy. At the same time, it can receive the energy from the power grid. So how does it work? Is that, as you can see, that the battery is charged during the night, because the time of use electricity price is very low during the night in Sweden. So during the night, the battery storage is charged, and then it's used to charge the bus during the daytime. So make the best of the difference in the electricity, make the best of the time of use electricity price, so we can reduce the operation cost for the electric bus. And the right figure shows the battery storage charging and the discharging profile. So the as you can see from the green bar, so the battery storage are charged by the renewable energy during the daytime, because we have the solar radiation during the daytime. But at the same time, the battery storage was discharging to charge the bus in different time of the day. So the energy supply to the electric bus system are from the renewable energy and the battery storage, and the energy from the battery storage could from renewable energy if the solar radiation is very high, so you can store some energy from renewable energy. At the same time, the battery storage will make the best of difference in the time of use electricity price to reduce the operation cost for the electric bus. And another interesting finding we have is that we consider the impacts of the charging demand from the electric bus on power distribution network. So in some vulnerable nodes, if there is without renewable energy, as shown by the blue curve, so the high charging demand in some peak hours in the charging point will result in the violation of voltage drop in the power distribution network, as shown by the blue curve. So the red line is the threshold, the lower bound of the voltage in the power distribution network. So if without renewable energy, high charging demand in short time, we will violate the voltage constraints of power distribution network. However, in the scenario with renewable energy, because renewable energy could be a complementary energy supply to the electric bus system, so we can satisfy that the charging demand, but at the same time to ensure it will not violate the voltage constraints of the power distribution network. So, and the right figure shows the final optimization results in terms of how many charger and how many renewable energy, photovoltaic, and battery storage we should install in the candidate charging point. So if I summarize it, it is that this research trying to optimize the charging infrastructure and the charging scheduling optimization for electric bus. And we integrate the renewable energy with battery storage as a complementary energy supply to the electric bus to reduce the operation cost, at the same time to avoid the potential violation of voltage in power distribution because of the high charging demand in short time periods. So this research is the methodology and the research contents can also be extended to other transport modes like freight transport, because of the violation issues of charging demand to power distribution network are mainly because of very high charging demand in short period. So for freight transport, so because of the high battery capacity of the electric truck, so you really need to provide very high capacity, very high charging capacity, and then it may result in issues for the power distribution network. So this work can also extend to freight transport. So this is connected research. Is more like a continuous research of the research I just introduced. So this research going a little bit further to share the charging station of the public transit to share the micro-community. So in this research, we are trying to optimize the shared bus charging infrastructure and the scheduling optimization, considering the renewable energy, photovoltaic, and also considering the sharing scheme to share the public transit charging station to share the micromobility. So the background is that when we do the first research, we realized that, okay, the charging demand from electric bus might result in the violation of the voltage violation in the power distribution network. So we continue to use the renewable energy as a supplementary energy supply to the electric bus. At the same time, we realized that even that we try to optimize the charging scheduling for electric bus to make the best of the charging infrastructure, but there is still some time window that the charging station in the charging point for bus are not fully utilized. So we are trying to seek why not to better utilize the available time window good sharing charging problem. So the current situation in Gothenburg, the city I'm in, is that there are very limited warehouse to charge the batteries of the e-scooter sharing. So the operator of the scooter sharing, they have to pick up the battery from the scooter and then go back to the warehouse to charge the battery and then send out the battery to replace the no SOC battery of the scooters. And it's generally resulting in very long detour because there are very limited number of warehouse for charging for a scooter sharing system. So why not trying to use the available time window in the electric bus charging point to charge the battery for a scooter sharing systems? So trying to make the best of the charging infrastructure for electric bus. So yeah, and the research aim, so we are trying to make the best of renewable energy as a supplementary energy supply to the electric bus system. At the same time, of course, we also optimize the charging infrastructure and the charging scheduling for the bus. But at the same time, we are trying to share the charging point from electric bus to share the scooter system so that the scooter sharing system operator can reduce the battery swapping and charging cost. So this will be involve the infrastructure decision for the electric bus in terms of number of charger and the capacity of charger, and also the required PV voltaic panels in each charging point. And for operation of the electric bus, we need to optimize the charging scheduling. For the shared micromobility operator, the scooter sharing operator, they need to decide how to, when and where to charge the batteries of the scooter sharing, making the best of available time window in the charging point for electric bus. And one research challenge here is that there is a conflict between the public transit and the shared micromobility operator. So here shows an example is that for the scooter sharing operator, of course, they would like to charge the battery in the nearby charging bus charging hubs. However, if in the nearby charging hubs there is no photovoltaic, that means that there is no additional energy supply because of the photovoltaic in the bus charging point. It will need the electricity from the power grid. So for the that is not that will not result in benefit for the public transit operator, but instead is that the public transit operator, they hope the shared scooter operator and they can charge the battery in the charging point with renewable energy, because the available time window from the bus charging point, they still have the electricity from PV. So the public transit operator can share the electricity from PV to the shared micromobility operator when the bus system doesn't need the electricity from the PV. So the shared scooter company would like to charge nearby, but the public transit operator would like the shared micromobility operator to charge in the station with solar PV. So there is a potential conflict there. So to solve this research challenge, we propose a optimization framework and B-level mixed integer and linear model. So formulate it as a neither and follow problem. So the neither problem is that the public transit operator to optimize the charging infrastructure, the photovoltaic infrastructure, and the charging scheduling for the electric bus operation. At the same time, it provides the available charging windows to the shared micromobility operator to give this available time window for the shared scooter operator to charge the battery there. But the optimization from the shared micromobility operator perspective will follow the decision from the public transit operator. And for the optimization, we consider different seasons, and because it will affect the charging demand from the e-scooter sharing system, and we also consider the charging demand variation in different day and different hours of a day. So this is a summary of the problem framework I just mentioned. And we use a solution approach called value function-based exact algorithm. So because we're trying to solve the problem for the case study in the whole Gothenburg, and then it will be pretty computation intensive. So to improve the computation efficiency, we propose a cutting methods to reduce the optimal solution searching space. We call it super valid inequity, but because of time, I will not go to details. And the aim of this strategy is trying to cut down the optimal solution searching space so we can reach more fast convergence to get the solution. So now if we look, we do the case study for whole Gothenburg with 70 bus routes and 61 bus terminals. And we have the data about e-scooter sharing in Gothenburg so that we can get the charging demand in different hours of the day and in different day of the week and in different seasons. We also consider the time of use electricity price when we do the optimization. And we divide the Gothenburg area into lighting e-scooter zones. So the zone is more about to gather the charging demand from e-scooter. So, yeah. And now if we look into the results, is that the right column shows the baseline scenario is that we do not install solar PV and we do not implement the sharing scheme to the scooter sharing company. That is the infrastructure cost, operation cost for the bus bus operator. Yeah, and after we install the solar PV, as you can see, it can reduce the overall cost for public transit operator by 10%. And if we include both solar PV and the sharing scheme to the scooter sharing operator, it can result in it reduce the cost, or you can call it profitability by 20%. And what is the benefit for the shared micromobility operator? So if we do not have the sharing scheme from the public transit operator, this is the operation cost for the scooter operator to charge the batteries. And if we have the sharing scheme from the public transit operator, it can reduce 54% of the operation cost for the e-scooter sharing operators. And this is trying to show the benefit from installing PV. So I will take the first figure as an example. So the red line shows the demand that we request from the power grid to satisfy the demand from both public transit and the shared e-scooter. And the green line shows the electricity supply request from the power grid when we have the PV. As you can see, installing PV will reduce the demand and electricity demand request from power distribution, and then it can reduce the burden of the demand to power distribution network, which is expected because the PV can provide some additional energy supply. And we're also trying to analyze that what is the benefit in terms of emission, and considering the greenhouse gas emission factors from the electricity generation in Europe. So the results show that if we install PV, because some electricity will come from the solar radiation, it can reduce the emission by 3%. And if we enable sharing and solar PV at the same time, so the emission impact will be very similar. So it will be also around 3%. So if I summarize it, and we are trying to implement the PV integration to provide additional energy for the electric public transit and electric shared scooter. And we implement the sharing scheme of the public transit charging point to the scooter sharing to reduce the operation cost. And we do the optimization and do the evaluation in terms of economic and the emission benefits by the proposed optimization strategies. Yep, thank you so much. And that is my presentation, and any question or comments will be welcome.
Thank you, Professor Gao. I think we can open for questions from audience. 当然我们也可以问问题，也可以中文，高老师也可以用中文解答。
好的。
高老师你好，我是那个香港理工大学工业工程系王坤。不好意思，因为那个刚才入会有点晚，所以有一些内容错过了。我也想问一个问题，我觉得您这个研究很有意思。我想问一下，那个 e-bus 的 charging， 跟这个 e-scooter 的这个 charging， 可以共享的时候，这个有没有一些 priority 的问题？像 e-bus 的话，它的 schedule 应该是比较固定的，而且可能是有一些 priority。我的意思就是说，那这个我们怎么 incorporate 进去，开放给 e-scooter， 就这个信息怎么样传导？谢谢高老师。
谢谢您的问题，就是第一个问题就是priority 的问题，就是我们把它 formulate 成一个 need and follow 的一个framework 的原因就是这个，就是 public transit 肯定是优先的，就是它要先满足自己的充电需求。只是把 available 的time window 开放给shared scooter， 然后呢，这个 public transit charging station 的共享有很多种策略，对吧？你也可以共享给那个私家车，但是当时我们为什么要考虑就是分享给 shared scooter 呢？其实scooter 的 charging 的它的 flexibility 比私家车要高，因为那个 scooter 是一个 battery pack。然后它换下来之后，它就放在一个充电箱里面充。那么呢，它没有严格的时间要求，说我一定要什么时候要把这个 scooter 的 battery 给充满。所以呢，它的充电时间相对比如私家车这种，它的这个flexibility 会更高。那么呢，就是 priority 就是满足 public transit 的充电需求，同时呢，把 available 的或者剩下的 time window 分享给 shared scooter。那 shared scooter 呢，它因为它是 battery swapping， 它其实是一个充电箱，里面放很多个 battery， 然后它在那充，然后呢，它对于这个充电时间的限制没有那么严格，所以是这么一个问题的 formulation。然后第二个问题呢，就是我们这个研究里面确实还没有考虑，比如说有一些 bus delay， 或者说因为比如说节单天气导致了 bus energy consumption 有显著的增高，那会导致你 charging 的 SOC 就是在那个充电站需要的充电时间更长。我们这个研究更多的就是在规划层面，就是还是基于正常的 timetable， 然后我们的 energy consumption 也是说把它简化了，用一个固定的 energy consumption 基于它的行程。 所以呢，这个 uncertainties in energy consumption of electrical bus 在我们这个研究里面并没有被 address。
好，谢谢高老师。
高老师，我可能一样的一个follow up 一个问题啊，就是比如说，那是不是我们那 e-scooter 它本身这种充电需求应该是不确定性应该是比较大的，就这种不确定性是否也能够被考虑在这个模型框架中？
对，谢谢王老师的问题，这个肯定是能考虑 uncertainty 肯定是更好的。然后我们在那个研究里面考虑的 uncertainty 一个相对简单的做法就是考虑了不同 season 不同天它的这个 scooter 的它的那个 charging demand 不一样。但是呢，在哥德堡它的 scooter charging demand 它对于这个它的充电的策略是。那个人去把 battery 拿下来，然后拿到充电站去充，然后在一个箱子里面充。那它并没有严格的那个时间要求，比如说必须多少时间把这个 battery 充满。其实现在欧洲这个e-scooter sharing battery 的充电，他们基本上要准备2到3倍的battery，相对于他们的车辆数，就是为了保证这个它能够保证那些车都是能够换到充满电的电池。所以就是它对于这个充电的时间，的 certainty 要求 ，scooter 对于这个 battery 充电的时间的 certainty 要求没有那么高，因为它有很多冗余的 battery 在那里。
明白，明白，感谢。好，看看其他各位老师同学是否还有问题。
高老师，高坤，我是飞熊啊。我有个问题啊，就是说你们做这个charging demand的这个规划，有没有考虑到这个 passenger demand？ 比如说 peak hour 的时候人很多 ，non peak hour 的时候人很少，尤其是在欧洲这种地方，可能是比较常见的。有没有解决这种问题呢？
谢谢廖老师的问题。在我们这个研究里面，我们考虑的思路还是就是传统的交通规划的思路，就是说，比如说我们知道一天它充电的需求肯定是一个 distribution， 因为天与天或者是 season 与 season 有一些这个variation。那么呢，我们可能就取最大值或者取比如85分位值它的 charging demand 作为我们规划的一个 input。但是呢，我们这个研究确实是在 planning 的这么一个层面的研究，并没有并没有聚焦到去 address， 比如说一天之内 peak hour 和那个非 peak hour 那个 off hour 它们之间这个 charging demand。那我们规划可能就 take peak hour 的 demand， 因为它是更大的需求，然后把那个东西作为一个我们规划的一个 input。但是具体到每一天里面的实时的调整，这个研究并没有 address。
理解。
好，看看其他还有老师和同学有没有问题。没有，咱们时间也差不多了。再次感谢高老师的精彩报告。谢谢高老师。
谢谢王老师。
行，好。Okay. So we end up with the first presentation. So next one will be a topic on the space-time prism accessibility and behavior activity traveled chains. And this talk will be delivered by Dr. Feixiong Liao from the Eindhoven University of Technology. So let me briefly give you an introduction to Dr. Liao. Dr. Liao is a tenured assistant professor at the Urban Planning and the Transportation Group at the Eindhoven University of Technology. His field of expertise and interests include urban planning, transportation studies, mobility and behavior analysis, demand management, etc. Dr. Liao has current research focused a lot of large-scale models on the urban transportation planning. So he's also an expert on the frontier of multi-stage super network modeling for independent decision problem. So Dr. Liao, the floor is yours. Yeah.
Yes. How I can share my screen?
I think at the bottom of the screen. Yeah. Yeah.
Now you see my presentation mode.
Yeah, got you. Yeah, you may start. Thank you.
Thanks very much for the invitation, and it's also a great pleasure for me to introduce my research here. My presentation topic is about space-time prism and accessibility and behavior. Of course, space-time prism is a topic traditionally in the time geography field. It's not so much in the transportation management or management in general. But when I explain it, I will unfold that this concept and then the modeling can still be applied for transportation planning and transportation management. And before I start, I also would like to briefly introduce my university. My university, Eindhoven University of Technology, is a relatively young university in the Netherlands, and originally it was just a training school for Philips, because Philips is home in Eindhoven, and there's a large demand because of the industrial sector, and then the training school has become a university. And in about 2010, I come here, and then at that time the students is only about 7,000, and just after a few years it's double sized, and for students it's still the majority are Dutch, but for research and staff the majority are international. And in terms of the strategic area for research and mobility and the environment is one of them, and energy, health, and future chips. And every one of these field is linked with a company behind. For example, mobility in the past, the TomTom, the navigation system, and nowadays is more and more replaced by mobile phones, but still they're a major partner in making the maps. And for energy, there's a company Shell for the fuel, and the health is also with the Philip Health. And with chips, of course, almost everyone knows it's related with the ASML for making the chips. And all because of a strong collaboration with industry, so TUE, over the years, it's always ranked first in terms of industrial collaboration. And for this presentation, all the materials can be found in the following publications. Actually, it's the intersection of two fields. One is transportation, one is about geography. And first of all, I would like to discuss what's space-time prism. Of course, in the online platform, I cannot have a kind of interaction with you to ask this. And I just disclose the answer. The space-time prism was proposed first by Professor Hagenstreet from London University, Sweden. The original idea is very simple. It's just given two anchor points, let's just say two fixed points, and one maximum travel speed and the minimum active duration for flexible activity, given a time budget. And then the prism, space-time prism, is the geometry object. It's like, can you see my mouse? So it's just geometry object. It includes all the space-time passes for conducting the flexible activity. And the projection on the planar space is in a shaded area. Is we can derive the 3D space for the prism. And of course, the projection is PBA. It include all the accessible locations with this time budget. Another time, the space-time prism is still a concept, and gradually people in different fields, time geography and travel behavior, they notice this concept and feel is so powerful to delineate the accessible locations and travel behavior. For example, still from time geography field, Eric Miner proposed the network time principle, because for the original space-time principle is not that realistic, because it's just in a planar space. But if we project this method in the transportation network, and we need to take into account the network travel speed. On the right-hand side, you see the network time principle. As it shows, it's not that expressive itself. So still, many people in the field still apply the method and the term space-time principle, including me. So I always quote space-time principle, although I do nearly all the work is over the transportation network. But nevertheless, there is a small group of people, they still do the theoretical extensions over the planar space. And how to derive that can be done from this inequality. Let's say ST stands for the shortest path or shortest travel time between x1 and x, and with its inequality, we can derive the network time principle. So you may wonder what space-time principle can be applied for. As I mentioned earlier, if we have the potential path area, so we can easily find which locations are accessible. So that means this tool, this concept or modeling can be used as a tool to measure accessibility. And as I also mentioned, child behavior field find this concept very appealing, because it can be used for travel demand forecasting and management. And in this talk, I will spend most of time to talk about the application for measurement of accessibility. If time still allowed, I will also discuss briefly about travel demand forecasting and management. So just consider, on average, a person spend many hours out of home. Here is a typical active travel pattern from a household. Just imagine the husband send the child to daycare, and then go to work, and then go to a restaurant nearby, and then go to work again, and go to shopping, and then arrive home. As we can see from this pattern, we can clearly identify the certain space-time principle. For example, on the right-hand side, the person go to a restaurant. The activity is anchored by 2 points. Actually, it's 2 points. It's 1 point. It's about workplace. But then there's certain budget, like 35 minutes going out for lunch. And then in the afternoon, the shopping activity can be also anchored by 2 locations. One is workplace, one is the home place. As you imagine, that this space-time principle really depend on the anchor points. And then we can find the literature to conclude this is that majority of space-time principle modeling address a single transport mode, a single flexible activity, a single budget, which is a time budget. And then I will discuss the extensions over these 3 directions. First of all, as I mentioned, the space-time principle is anchored by 2 fixed locations. And then the traditional way is to extend it for daily activities. For example, here, if we consider multiple anchor points, the typical method is like to make building blocks. We have a space-time principle 1, principle 2, principle 3, and principle 4. And of course, this method is really dependent on the predetermined activity sequence. But if we look at the measurement, the accessible space, this method comes with a limitation, which is underestimate the space-time principle and potential pass area. And still, this method, the building blocks, is widely applied in time geography and for travel behavior. And of course, researchers notice this limitation, and then there are some proposed method to address it. For example, this is a method proposed by Professor Guan Meipo and her student. And the method is simply to enumerate all the possible activity travel patterns based on the varied sequences. And of course, this method, in theory, it works, but computationally is inefficient. And as you may know, that for this method for apply for space-time accessibility for large area, and is considered the agent is like millions of agents. It's almost impossible to apply this method because it's considered the calculation of travel time, shortest travel time between every pair of locations in the system. And there's another method proposed by Professor Anthony Chen and his collaborator. The method is to intersect the activity-specific feasible space-time region. Given that accessibility to a location need to respect the time window. So with that time window, we can define the earliest arrival or latest departure. But if we intersect one locations, one activities, there's a problem. Is that for an individual conduct daily activities, there's a total time budget. And then if we intersect all these activity-specific regions, there's a potential to overestimate the space-time prism and potential pass area, because the single activity-specific regions doesn't take into account the time that should be deducted by conducting other activities. And then I came to this problem, and I noticed the issues with the existing problems. So then I try to use the multi-state supernetwork that I have been doing research for a long time. And the reason is that I realized there's a lack of expressive presentation for this problem. So I think a multi-state supernetwork is an ideal one. How to do that is to just to consider a person in the beginning going out from home to assess all the activity locations and the travel links. And then at every point in the middle, we have an estimation to the destination. And with that, so we can define how much remaining time budget is available. So with that, we can delineate the potential pass area. But this method also only produce approximate space-time bounds, but is not construct the precise prism and the potential pass area. So then I realized that's the problem because from the unidirected search. So how about we conduct the search bi-directed or bi-directional? And it turned out we can find a precise space-time prism and the potential pass area. Here, the first one is a two-stage bi-directional search. And then I also propose like a very naive simultaneous bi-directional search. And also there's a goal-directed simultaneous bi-directed search. So these shapes with the different colors, for example, the gray area, the pink area, and blue area corresponds to different search space. I'm not saying one method is definitely better than other methods. It should be dependent on the extensive experimental analysis. And then here, the advantage is that it's precise and it's also computational efficient. Here is an example. Let's just consider a person conduct out-of-home activity with endpoint home and the activity at a workplace in W here. And just imagine that person have two flexible activities with shopping and leisure. And then there are three activities. And if we consider the active sequence, so there should be 2 power 3, there'll be 8 active sequence. And if we consider the time window constraints, let's say the leisure should be done after lunchtime. So then that will reduce a little bit the active sequence. So in a multi-state super network, there are 6 states, and if we apply different such method, and then that comes with different such space. In the first column is the real potential path area, and the first one is a naive simultaneous bidirected search. And then on the other columns are go direct search. One is with the A star, and one is a landmark method. As you can see, the right 2 columns represent the better method to find the potential path area. And with this, we can conduct large-scale accessibility analysis. And then the second extension is to extend to multiple transport mode, or in short, multimodal. In the literature, there are not so much research about it. It's mainly deal with by only public transport or by car, or just by walking and a car. And for that, the trip chain is relatively easier. But if we consider a multimodal trip chain first by private vehicle and then public transport, so there is a constraint is that person should go back to the place where the car is parked or the bicycle is parked. If we consider this constraint for the trip chains, and if we consider the network representation, there are a lot of multimodal trip chains caused by the flexible PV and PT. So our task is to find efficient solutions that can still find the potential path area and space-time principle. Here in this study, we propose 3 strategies. First is a upbound PPA. Second is a network partition. And lastly is a triangle diagonal inequalities to prove the selections. First, with the upbound PPA, this is quite straightforward, because as I introduced in the beginning, that the PPA was constructed by the maximum travel speed. So if we use the maximum travel speed to construct the PPA, of course, those locations that are out of the upbound PPA should be cancelled out. So this is very straightforward. But with this method, it may cause a large redundancy for choosing the locations. So then we suggest the second strategy to use network partition. If we just use the square grids to partition the network, and then the grid length, it depends on the PV, the private vehicle dependent speed. For example, if we have for car, the grid length may be longer. If we use bicycle, the grid length may be short. But you may wonder, if we use bicycle, there will be many grids. But actually, if we use bicycle, there is a certain limit of the travel distance by bicycle. But still, with any PV private vehicles, the grid number of grades are relatively the same. Okay, and based on this, and we choose locations that ideally for the private vehicle and public transport trip training. Just for example, in grade 1, if there is no public transport for training, so of course this grade is not relevant. And then in grade 2, we just choose a stop or station that have the most possible connections with other public transport routes. For example, in this grade, if all the public transport stop have 2 connections, so it's just a randomly pick one. And in grade 3, if public transport stop have 5 connections, we just choose this one. And then of course, in grade 4, and then there's 2 with 3 connections, because since 1 is covered by a non-stop in grade 3, so then we just choose the other one. And with this, we select a very limited set of ideal locations for PV and PT trip training. And then we just use the triangular inequalities to prove some selections. And this is also straightforward, but it turned out that this method can only reduce only a small set from the other compared to with the other method. So then I do a demonstration of the performance. Just consider the transportation network in the Eindhoven region. And then we consider 3 typical cases, and then we apply the strategy 1, strategy 1, 2, strategy 1, 2, 3. And then this column with my mouse is the selected locations for private vehicle and public transport trip training. As you can see, it's like only a small part of a original public transport stop. That's about 747. So you may wonder, this is really reduced the set of public transport stop. Will the result be reliable for delivering the potential pass area or PBA? But it turns out that the result is quite good if we consider the number of locations and accessible in the area. So almost it's like the noise is 93%, and for all other cases is near just almost the same. And but if we check the speed up factor, it's very high. It's like the noise is 44 times faster if we don't apply this method. That means this method means big potential for large-scale application. And then we also do a kind of empirical study for the Rotterdam region. And this is a study area, and here is the result. And the grade 9 denote the trip training by car and public transport. Just assume that everyone is with a car. And then the green curve during the real accessibility, in this case, that is considered the realistic ownership of car. And in the sample, there is about 70% of the sample are with car ownership. So with this result, we can say the car ownership definitely means higher accessibility. And of course, if we check the spatial locations of this area is in the x-axis. In some of the area, the accessibility is relatively lower. For example, number 23 is it's a city in this map. 23 it's in two diameter, so it's a city, small city, located between Rotterdam city and the capital city, Den Haag. The number of the reason can be that in this area there are a lot of people living there with high mobility, so they are not like permanent like a household people living there. And for these people, they normally don't have a car ownership. And then if we see the Lorentz curve for inequality analysis, and if we check the green curve, the real accessibility, and compare with the one only with the actual ownership of car and bicycle. So that means the public transport and the private vehicle traffic chaining can actually improve inequality of accessibility, although the margin is quite small. Okay, and then I would like to discuss about the extension to multiple budgets, because this concept is originated from time geography. Of course, time is very important. And then if we want to study child behavior, of course, the other constraints budget are relevant. For example, monetary cost. And if we check the literature, there were not so much research about it. Actually, there was only one we find it, which combines time, money, and emission budget. Actually, this is a study proposed by Professor Zhou Xuesong and his student. And the common knowledge is that if we have multiple budgets, the final space-time prism is just to intersect the prism of different budgets. And actually, this study by Professor Zhou also applied this method to find the final prism with multiple budget. But actually, if we look closely, it's wrong. And we just check this simple example. Just consider time budget 20 minutes and the monetary budget 5 euros, and this in this network with 12 time and the 12 cost on the network. And if you see the right hand side, the intersect method result in the blue like a prism with money and the time. But if we apply for the bi-criterion method, actually the space-time prism and the space monetary prism is much smaller. And if we change the two criteria at the same time, there may be no locations in the prism. So of course, then we just propose a method with the bi-directional bi-criterion search in the extended network. And here is a demonstration. The area delineated by the red dashed curve, the circle in subfigure A, so it's in the intersection. And the yellow area in the subfigure B, actually, this is the space-time prism and with the space monetary prism. So I see something. I don't know. I still have time.
Yes, you still have I think 10 minutes.
Yeah. Okay. Yes. Good. Yeah. I thought it's kind of a reminder about the time. Yeah. So we also did some empirical study in the area of Eindhoven region, and we just find a good case. Just say we introduce the mobility as service in the region, and of course that's very relevant because mobility as service is a very strong component with the monetary budget and with different price bundles. And then the result turned out to be that if we don't consider the monetary budget or constraint, and then the space-time and the prism and the accessibility is very likely overestimate. So that's also very relevant conclusion for transportation planning and it's very necessary to consider the multiple budgets for accessibility study. And then here is also a result for Lorentz curve about the inequality. If we check the curve with the SDP without mass, so that's the red one. So in subfigure A, actually the inequality is inequality is higher without the mass. But if we check the subfigure B, then with the mass, the inequality is lower. So of course, this is two scenarios with different pricing bundles, and this result tells us that mass can be very helpful to reduce inequality, but it should be carefully designed with the pricing bundles. And then, yeah, so since we still have some time, I would like to discuss about the space-time prism and its application for behavior and traffic demand. And I just showed this typical actual pattern in the very beginning. And here, the question is how we can apply this space-time prism as a tool to model the actual behavior in space and time. And for multimodal and multi-activity, this is come with a multi-state supernetwork representation. The good thing of this network representation is that any path through the network represent a valid or consistent actual pattern for conducting the daily activities with multi-activities and multiple transport mode. So that's the nice thing of this framework. And for its application for activity-based traffic demand modeling, and typically we just say for every link in a multi-state supernetwork, which just define a link disutility, and the X represent the time and the monetary cost and the convenience, the attributes of link, and beta, they can be the corresponding efficiencies. And these betas are typically estimated by like choice models, like random utility maximization models. And we can, with this link disutility defined, we can find the path with the least disutility for person or for agent. And then in that sense, we can have the actual patterns for the disaggregate people for study area, and then we can combine that output into time-dependent OD matrix as input for dynamic traffic assignment. And then this is a connection between disaggregate and aggregate. And this mechanism is typically applied by medicine. This is one of the largest traffic demand system is in the act-based modeling, and many cities try to apply this framework. So for me, as a modeler with a multi-state supernetwork, it's relatively straightforward for me. It's also to consider the scheduling outcome with multi-state supernetwork and just plug in all this OD trip matrix into DTA. And then I have a model system that can be comparable with medicine. But that can be problematic if we consider from traffic behavior modeling perspective. Typically, if we consider the link disutility, that should be with the error term here. Because as a modeler, there's always a problem with unobserved things in the disutility. But in this model system, what I have over the years is without this error term. And then without error term, it's fine to be used for recommendation. Let's say we have a advanced activity travel scheduling system for or assistant for a person. So we just recommend you to do certain things, but it's not really for forecasting. So this is the debate that I always receive or I had with other travel behavior modelers. So of course, for me, it's very like motivated to incorporate the error term in the modeling of this. And here is this typical case for node choice. If we don't consider activities, we just consider trip. It's just a node choice model. And typical one is with have a term theta to denote the perceived cost or the level of perceptions on the network. And with that, we can still apply the multiple normal logic model to have the error term incorporated. And of course, for that, is need to calibrate theta. And for this line of research, you need to consider the universal set U, and then we need to have a choice set generation mechanism for that. And with that, we also consider a consideration set for node choice. Okay, so of course, for applying with the error term in the forecasting model, we need to have a node choice set. Just as I explained earlier, that the space-time principle can be applied for delineating the accessible locations. Of course, we can also extend to accessible locations, accessible nodes. And how to do that? We just consider to have the choice set generation for actual patterns of through the multi-state supernetwork. And one issue popped out is about many of these generated actual patterns have a high overlap. And then we need to apply certain method that can correct these overlaps, such as chain logic, path size logic, and etc. And we also did a study and applied in the Eindhoven region. We just connected data from over 300 individuals' daily GPS trajectories. Then we have the daily active program. And at the same time, we find the data about the location attractiveness. Because for travel demand forecasting, we should also consider locations. It's not just about people always choose the shortest travel time. It's also about the locations. So some locations are better, and then people can trade off with travel time. So the next thing to do is to simulate, to use the multi-state supernetwork based on the method of a space-time prism to generate the active travel patterns for generation, and then to apply the choice model method for estimation. Now here, briefly, I show the result with a different estimation method. And it turns out that path size logic and the path size logic with extension of overlap on the temporal dimension. These two methods, estimate methods, are the best compared to others. The reason why we consider the temporal dimension overlap because is that if we consider the active travel pattern, people may stay in the same location or go through the same route, but then the tempo may be different due to the time and the sequence, active sequence. So if we don't incorporate this temporal dimension overlap, that can also have kind of overestimation of the path size logic. So as you can see, these two excelled in a like a model fit, R-square, and BIC. And here is the estimation result with different coefficient such as constant, and then the travel time, and then the coefficient for land use and the location attractiveness. And as you can see here, the R square by part size logic with a special consideration of tempo overlap is the best. And one thing we still need to figure out is that the constant here is relatively high, and so this may be one issue. But other coefficients are also significant. So that's something we will figure out before we submit this ongoing work. And then I discussed about the activity scheduling and also the activity scheduling result for activity implementation. That's typically called traffic assignment. And then the next step, I may also want to apply this space-time principle method for activity generation for an individual. That means that for this current method, we still assume that the individuals already given their activity programs. But then it's also possible that people, they have the activity changing day by day. So I would like to apply the space-time principle for activity generation. And then if we go one step further in the model chain, we should also consider the population generation. And this related to the large scale or long-term decisions such as housing and job mobilities. And with that, I can say this model system is really powerful that can incorporate long-term and short-term decisions. And with that, I would like to close finish my presentation. Thank you very much for your attention.
Yeah, thank you, Dr. Liao. It's a perfect timing. Thank you for this great talk. Now, let's open the floor for the questions from the audience. 各位老师和同学也可以问问题。对，如果那个有高老师，
对，廖老师好，谢谢您的精彩演讲。我有个就是相关的问题，就是现在在瑞典那个Swedish Transport Administration， 他们对 accessibility， 他们除了 objective accessibility， 他们也对那个 perceived accessibility 非常感兴趣。这个两个问题就是您的这个刚刚讲的这个 framework 能把这个 perceived accessibility 也融入进去吗？或者说这是第一个问题。第二个问题就是您对这个 perceived accessibility 相关的研究，您的这个看法是什么样的？
高老师，谢谢你的问题啊，非常好的问题。因为实际上，我们前段时间正在准备做这个 modeling extension 到 perceived accessibility 啊，这个话题也非常的火吧，大概已经有5-6年了。大概在新冠前嘛，我在一次那个 conference 这个会议上就听到有人在讲，然后主要是我们这边荷兰几个老师，戴尔福特的几个老师，还有格隆尼根的老师，他们率先提出了 perceived 的这个 accessibility。然后我觉得就是在我们这个 framework 里面是可以的。在目前来说，我都是一些 objective 的 measurement， 是吧 ？travel time 啊 ，travel monetary cost。如果说我们把这个人的 perception 考虑进去，就是变成了一个 perceived。但是这样的话就非常依赖于很好的数据，然后去标定，去做这个验证。这一块还有就是我也想提到一下，就是说 space-time principle 呢，是目前是做 accessibility 的，大概一小块。目前主流的还是做这个 place-based 的 accessibility， 就是说我家住在哪里，我家方圆几公里之外，然后有超市，然后有工作的地方，有这个 park， 有这公园，然后它不能很好的考虑到这个就是说每个人的 heterogeneity， 所以说后来为什么把 perceived 考虑进去，就是为了去解决这个弊端， perceived place-based accessibility， 就把一个很容易让人家能够懂的，并且很容易执行的，然后又可以把一致性考虑进去。然后 space-time principle 呢，很早之前，因为它说是 agent based， 就是 individual based， 所以它可以很好的解决 heterogeneity， 这就是它一直以来的一个优点。但是它这个东西就不是很好沟通，跟人家去表达，因为它因为做这个规划了 transportation planning 呢，它一般它对这种模型的表达还是理解，就是或者说我需要更长时间理解的话，我就不理解了。所以说我感觉我就想在这方面去赶紧去推动，把这个 perceive 的也加进来。然后这就是我目前的一点理解吧。然后如果你对这个方面研究感兴趣，我感觉可以参考就是那个 Better One Way 他的一些 review paper， 他很早就提出了 perceived 的 accessibility。
谢谢老师。对，我跟他们就是也有一点点相关的讨论，也就是说这个主要的问题还是没有数据，这个 perceived accessibility measure 呢就很困难。然后呢，
对，
最好是能够把 perceived accessibility 和 objective accessibility 建一个模型，能把它连接起来，这样呢 objective 的 accessibility 某种程度上能够用到去 estimate。当然了，现在这个数据确实很难获得。
对，尤其是现在这些 mobility 数据，它都是day by day 然后前景的，对吧？比如说我今天感知是这样子，我明天感知是另外一个。然后传统的 accessibility measurement， 它就是说我做规划的时候，我就考虑一次就做好这个规划。但 perceive 的话，它更复杂一点点。所以说这个对数据的依赖，然后会更大，然后对模型的这些挑战也会更大一点点。
好，谢谢老师。
对，我可能一个小问题，然后说我也在想那个数据的事情，是不是我在想手机心理数据是不是一个比较好的去 calibrate 这个 model 的数据？
手机心理数据就是说，它首先它规模很大啊，这个是很好的，但是就是说它，在我们这里就是尤其是精确的个案都会找到很具体的 pattern，具体对于哪些 location 的感知，然后那个心理数据的话，可能它就那个处理度就太粗糙了，然后就需要做很多推断。我不是说不可以，就是说这个数据上也是可以，就希望对模型上有更多的挑战。然后如果数据很好，比如说直接是很多天的 GPS 数据，然后把这数据全部整合在一起，然后我去把每个人的 perceive 的估计出来，那就是对方法上，那个依赖性没那么强，然后但是结果也可能会，更直观一点的吧。
明白，感谢，对，非常感谢您的精彩报告。可能我们时间也差不多了，就可能也没有时间讨论更多问题，后面看看。可以再继续和您交流，包括微信交流，那个 email 交流也可以。
可以。
好嘞，
谢谢啊。
行，好，感谢，谢谢梁老师。好，那最后一个报告就是咱们的李老师李昆鹏老师来自华中科技大学的，然后李老师是华中科技大学管理学院教授，长期从事供应链管理、物流管理、运营管理方面的研究，包括一些教学的相关的咨询工作。在国内外的主流期刊，包括一些顶级的期刊，包括EGR，发表论文大概50多篇，主持多项国家基金委的面向项目和企业咨询项目，包括一些相关的企业，包括中国交通建设集团，中船动力集团、3家集团等。然后今天李老师带来的报告是 Framework Model Algorithm for the Global Control of Urban Automated Drive Traffic。李老师，那下面就邀请您来做报告。
好嘞，好，谢谢主持人。好，那么这个大家可以看到这个视频吗？
要是那个 PPT 好像还没分享。
马上啊，
视频能看到。
好，这个就是好，这个可以看到我的这个PPT 吗？
可以，李老师。
好，谢谢啊，谢谢王老师。好，这个非常感谢大家啊，这个非常晚了，还有这个大家有时间来听我的这个报告啊，这个我会讲的稍微快一点点啊。那么今天我要跟大家分享的这个题目是在自动驾驶背景下，整个城市交通网络 这个全局控制的框架啊，这个模型这个模型和调度的这个相关的这个算法。那么今天的这个报告大概分为6个部分啊，首先是这个背景的部分。那么对于目前来讲啊，最近这个自动驾驶啊，大家非常是关注。那么对于自动驾驶的这个它的这个级别的这个分级啊，一般分为5级。1级的话呢，就是还是以这个驾驶员为主，但是呢，车辆会给驾驶员提供一些提示。那么2级的话呢，就是车辆啊，它会一段时间啊来这个辅助驾驶啊，驾驶员也会驾驶。那么这个就是一种这种共同驾驶的这个模式。那么驾驶员他可以temporarily 啊，就是临时啊，我这个手可以离开方向盘。那么对于 Level 3啊，应该来讲就是大部分时间是由车辆的这个自动驾驶系统去控制这个车辆。那么这个驾驶员只需要在需要接管的时候去接管这个车辆就好。那么对于 Level 4的话，理论上来讲啊，绝大部分时候是车辆自己自动驾驶。那么对于这个驾驶员来讲啊，他需要坐在这个主驾位上啊，可能会处理一些突发的情况。对于 Level 5来讲啊，基本上是所有的时候这个车辆是自动驾驶啊，这个驾驶员他也不需要去坐在这个驾驶位上。那么对于目前来讲啊，目前像一些主流的这个厂商，像这个比亚迪、华为啊、理想、小鹏、小米和蔚来等等这些车企，他们所推出的这个自动驾驶的这个系统，严格上来讲，基本上都是属于这个 L2 的这个级别。那么对于这个高等级的这个级别的这个探索啊，像这个梅赛德斯奔驰啊，在探索这个 L3 的这个产品。那么对于这个我们可能大家已经这个比较熟悉的百度啊，百度的这个萝卜快跑这个系统来讲，它是属于 L5 级别的这个驾驶。我们在像我们武汉呐像一些城市我们看到的萝卜快跑的这个车辆，它是没有驾驶员的啊，所以它应该是 L5 的这个驾驶的这个系统。那么这个时候就有个问题了啊，就是随着自动驾驶技术的演进和各个厂商都推出了自动驾驶的产品，而且也产生了一些问题。那么这个时候作为这个政府和相关的部门，那么在制定一些这个政策的时候就有很强的这个指导性。也是同样是这个月啊，这个我们的这个工信部就制定了相关的政策，就规定那么所有的自动驾驶车辆的自动驾驶的产品在推出市场之前必须要经过严格的完整的测试啊，这也是针对前期发生的一些问题。第二个呢，就是这个厂商必须要声明啊，我这个自动驾驶技术它的这个功能的边界和特别是产生了一些安全性的问题的时候，那么这个驾驶员和厂商，也就是车辆之间的这个责任划分如何划分的问题。第三个呢，就是厂商不能够去夸大或者说误导这个宣传啊。可能这个前段时间大家也知道，网上很火的一个事情啊，这个也是因为这个实际上发布的是 L2 的这个产品，但是呢，可能有很多的这个因素啊，造成了这个消费者他把它当做一个 L3 的这个产品在使用，结果就出现了一些问题。好，那么也就是在这些背景下，我们要问2个比较重要的问题。第一个呢，就是随着自动驾驶技术的普及，那么未来城市交通它会像什么样子啊？也就是说，未来我们开我们的车到街上去，我发现周围全是自动驾驶的车辆，那这个时候我应该如何驾驶我的这个车整个的这个交通状况它会是一个什么样的状况？第二个问题就是从政府和监管部门的这个角度来看，那么未来随着自动驾驶车辆的逐渐普及，整个城市交通的网络它应该如何去控制、去管理去优化这是我们必须要回答的2个问题。那这个时候我们就总结和提出了2种总结了2种这个整个城市交通网络控制的模式。一种就是我们当前的叫做局部的这个控制和调度的模式，也就是说，不管是我们的目前是驾驶员，还是这个我们推出的各种自动驾驶的产品，它实际上它是一种局部驾驶调动的这个模式，也就是这个车辆它只是根据我当前这个车辆所处的前后左右的相关的这个相应的这个信息，比如说前车跟我的距离，左车跟我的距离等等，这些做出当时汽车控制的这个指令。 第二个呢，就是我们在规划我们每个车的这个路径的时候，还是我们驾驶员自己去规划这个路径。那这个时候就有个问题，就是比如说，我们在规划路径的时候，发现一辆一个路径啊，它非常畅通。等到我们走过去的时候，我们发现实际上已经堵车了。为什么呢？很可能在规划这个路径的时候，大家都在规划要走这条路，因为当时这条路是比较畅通的。结果我们去了之后就变成拥堵，这实际上就是一个整个的这个路网的这个资源分配不均的问题啊，它容易导致这个交通的堵塞。好，这个时候我们就这个有另外一种模式啊，就我们提出另外一种模式，叫做全局调度的模式。这个全局调度的模式是整个这个路网它是由一个中央的控制平台去控制。这个平台它要负责为这个路网中当前所有车辆去规划他们的路径，同时要去负责控制所有车辆的这个驾驶和动作这样的话呢，这个整个的这个网络它的这个车辆的路径车辆的控制，它是基于整个网络的全局的这么一些这个信息去做的规划。这个规划就应该来讲会比这个我们讲这个局部的这个控制的模式要好一些它有很多的这个好处。好，目前这个模式基本上这个大家这个对于整个城市交通网络来讲，提出这个模式还比较少。那么有很多人会问那么我们目前的这个技术是不是有可行性基本上从目前来看，我们的技术已经有了很大的这个可行性去这个 support 目前这种全局的这种模式比如说这种模式需要有非常精准的对于当前路网状态的感知和驾驶这个车辆的这个状态的这个感知。那么这个我们目前有很多的这个产品很多这个厂商的产品都推出了有很多的摄像头，很多的这个激光雷达，很多的这个传感器的这么一些这个车它可以准确的去识别路网和这个车辆的这些信息。同时的话呢，我们这个车上还有很多的这个芯片，我们有很多的这个系统可以实时的为这个车辆做一些智能的这个决策所以这是第二个这个决策的问题。第三个呢，就是路径的规划问题它依赖于高精的地图依赖于实时的这个信息的这个传递等等这些我们也有非常成熟的产品。那么还有一个呢，就是车和车之间的通信，也就是我们目前这个车和车之间是没有通信的，那么未来车和车之间要有这个通信和沟通的交流这个利用一些通信的技术它也可以实现包括这个交通的这个规则和信号灯的这些控制等等，这些从这个技术上来讲都是没有问题的。那么我们来看一看这个百度的这个产品百度的这个萝卜快跑的这个产品，实际上这个已经有测试有一段时间，像在我们武汉已经投入了这个商业的这个运营。通过这套系统，实际上我们看到它是一个有一个前台有个后台的这个系统。前台就是我们所看到的在路上走的这个萝卜快跑的车，后台系统它实际上有个非常庞大的控制的这么一套系统后台有这个远程的驾驶员它可以去监控去控制这个车辆的这个行驶。但是这个时候我们就可以看到它实际上从这个技术上已经具备了这个前台和后台控制的这么一些功能从前台来讲，它可以实时的通过这个车上的各种的这个设备去感知这个车和路网的这个状态那么这是这个感知。那么从这个后台的控制来讲整个的这个后台它可以去比如说对于萝卜快跑它所属的这些车进行一个全局的这个调度同时对每一台车也进行这种控制。那未来我们可以想象一下，如果像萝卜快跑这套系统升级为整个城市的交通的这么一套系统的话，其实它是可以去负担比如说这种我们刚才讲的这个全局控制的这么一些功能。好，那么我们稍等这个好，那我们来看一看这个全局自动驾驶的这个控制和驾驶的这种模式到底有什么好处去行驶大家我这个在我们传统的这种当前的这种驾驶模式下是不可想象的。我们如果说是时速100公里每小时，那么我们肯定要保持起码50到100米的安全距离。那么从这个角度来看，我们可以看到这个整个城市的交通的容量会极大的这个增加，比如说估算会有一个翻倍的这个增加。那么 这个整个交通的拥堵可以减少大约30%啊。同时的话呢，它可以让我们的这个整个交通的调度有更强的灵活性。比如说我们有这个警车、有消防车在出任务的时候，那么这个它就可以具有优先的通行权啊，由这个全局去控制啊。同时的话呢，这个一旦路网发生一些紧急的这个状况，也可以及时的去处理啊，都可以依赖于这个全局的这个调度的这个网络。同时整个网络有更高的安全性啊，因为这个信息的感知、这个决策的这个制定的过程，它具有更高的效率啊，相对于人来讲。好，那么这个系统，这个全局控制的系统是否有很好的这个可行性和这个应用的这个可能性呢？其实我们可以从另外一个系统可以看到这个应用的这个前景啊，也就是这个在很多智能仓库中啊，实际上已经用到了这一套技术的整个的这个原理和控制的过程啊。最有名的就是亚马逊的 K 法系统。在这个系统中，它实际上是在智能仓库的这么一套系统里面在应用。在智能仓库中，它是这种3格式的单向道的这个路，它实际上跟我们现在很多城市的以街区为这个主要布局方式的这个井字形的这个路有很大的相似性像我们华中科技大学，我们的这个路也是非常规整的这个井字形布局的这个道路，这是一个。第二个呢，就是在这个仓库里面的这个机器人它就是采取全局调度的这种方式这个有一个中央控制的这么一个平台去控制每一台机器人它的这个它的这个搬运它的这个路径等等这些方式。所以这种全局控制的方式已经在智能仓库这套系统中已经应用的非常的成熟。那么目前来讲，这套系统它的效果也非常好它可以让这个订单处理的这个效率提升让这个比如说这个拣货的这个效率可以有3倍以上的这个提升让这个库存周转能够加快等等这些好的这个表现。那么我们这篇文章主要做什么呢？这篇文章我们主要研究在整个这个未来全局控制的这个城市交通网络的这么一个场景下，如何去控制每一台车它的这个路径，它的实时的这个行进的这个指令行进的这个如何去避撞等等这些工作。所以我们主要是首先提出了这个全局城市交通网络全局调度的这么一个模式，然后呢还提出了一个分区的这个概念这个刚才廖老师也讲了这个分区的这个概念，就是在整个城市未来的这个交通网络中，这个网络非常之庞大。那么我们要用这个一套系统去管理这个网络可能不太现实，那么我们就要进行这个分区的这个管理分区里面它是如何管理的，区和区之间它是如何协同的我们提出相关的这个机制。然后我们把整个的这个刚才我们讲的这个分区控制的这个问题把它用这个混合整数规划的模型建立出来，然后用这个改进的 A 型算法去求解这是我们这篇文章所做的主要的工作。好，对于这个文献综述这一块，我们综述了过去10年我们查了过去10年在 Web of Science 里面用自动驾驶相关的关键词收了差不多超过1000篇 paper。那么我们发现80%以上的这个文章，它主要是关注于自动驾驶的技术也就是技术的这个研究。那么非常非常少的这个文章在讲整个自动驾驶系统它应该如何去控制特别是涉及到这个城市交通系统的这个控制就更少了所以这是我们这篇文章想去在这个领域去深度做一些工作的这个原因那么我们第二个部分就是全局自动驾驶调度的这么一个模式实际上这个模式刚才也稍微介绍了一下在这个整个的网络中，比如说我们的交管局它有一个全局控制的这个平台，它负责去控制所有的这个实时去控制所有的这个车辆。那么这个平台也要实时去收集整个路网中的相关的信息比如说整个这个交通的状况、车辆的信息等等 然后实时去调度路网中的这个车辆啊。所以这个是整个全局自动驾驶调度的这个模式要做的事情。那么首先那么这个它要进行这个整个网络中对所有车辆进行统一的这个调度目前我们的这个局部的这种驾驶调度的模式是每个车自己去做这个决策所以说这个是要全局去做这个决策也就是说未来整个网络中的车辆的这个控制权它不在这个驾驶员手中也不在车辆手中它是在这么一个全局的交通网络的这个管控平台的这个手中。那么我们看，比如说以北京市或者武汉市上海市等等这些比较大的这个城市来看的话，如果我们整个城市交通有一张网一个平台去控制，可能目前来讲，以目前的这个问题的复杂度，目前软件、硬件和算法的这个速度来讲，可能还达不到。那么我们就提出了一个分区的概念，也就是把整个网络分成若干的子网络，每一个子网络的这个模式，也就是我们前面讲的这个全局控制的这个模式。那么它的具体的这个控制的方法可以是我们提出了一种可供大家参考的这种方式比如说以时间一段时间一个时间区间为单位比如说这个时间区间可以是50秒30秒可以是1分钟或者是2分钟。那么在一个时间段内车辆会提交它的这个入网申请，也就是你未来要进入这个路网的时候，你不能像现在一样，我开到街上去我就进入了。你首先要提报你的这个起始点的需求，那么这个整个的这个网络它会接收你的这个数据，然后进行这个计算出你的这个路径那么你给你这个路径，然后你这个车再进入这个网络那么在网络中你的这个行驶状态它会监控你的实时的这个运行的这个方向和轨迹，它要去控制等等这些包括比如说像这个在交叉路口的为了避撞你要等多长时间等等，这些都是由这个平台去计算出来，然后对你的这个车辆进行这个控制。好，那么还有一个就是我比如说我的这个车从城市的一边到另外一边的时候，我肯定会穿过多个子网络，那这个时候网络和网络之间它就也有一个交互的过程。那你从一个局部网络出来的时候，这个时间和你出来的这个地点，它就作为这个输入数据，这个进到另外一个相邻的这个子网络，它就作为输入数据去规划你在下一个子网络中的它的这个行驶的这个路径。这是我们整个提出了一个供大家参考的这个整个的这个网络也就是交管平台他们控制的这么一个流程，大概就是车辆去提报这个入网这个申请它的这个起始点，然后等到这个时间片区的这个开始下一个这个时间片区开始的时候，就把你这辆车和已有的网络中的这些车一起进行这个调度然后得到你的这个计算得出你的这个路径之后，再发送到这个车辆，发送控制指令到车辆上去控制车辆进行这个行驶到了每一个交叉路口的时候，还要进行相应的这个避撞的这个控制等等，你这个车辆按照正常的这个情况去行驶，直到你的车辆离开这个网络。那么如果有一些紧急情况的发生，比如说发生了交通事故有一些突发情况等等，那么就马上进入这个紧急事情处理的这么一个流程大概是这么一个过程。那么在这个整个的这个网络中有一个非常重要的要处理的这个问题，就是避撞的问题。那么我们主要是通过这个优先级和这个调度规则去处理这个避撞的这个问题我们目前交通网络的这个避撞它主要是通过红绿灯也就是信号灯和通行的规则，比如说转弯让直行我们都要靠右行等等这些规则去进行这个避撞的这个操作。但是未来的话我们很可能在全局调度的网络中很可能就看不到红绿灯了因为这些控制的规则它已经写到了全局调度的平台的算法里面去了所以这个时候就没有必要在路网上去设置这个红绿灯。那么基于这个优先级规则那么我们设定了有车辆的优先级比如说特殊车辆、警车、消防车 救护车它的优先级要高于目前的正常的这个行驶的这个汽车，目前在我们这个网络中也是一样的。那么我们有道路的这个优先级比如说这个车辆负载比较多的道路，可能它的优先级要大于这个负载少的这个道路等等通过这些我们进行这个避撞的这个操作。好，下面我们的这个问题的描述是这样，就是在整个的这个我们以这个街区式布置的这个场景为主有很多3格式的这种路径那么这个在这个路径中，我们有很多的这个车辆那么也有很多的这个路径最大的一个特点就是有很多的交叉路口。那么在这个交叉路口这个避撞的操作就比较复杂一点。好，我们的这个模型的要决策的就是在整个路网中每辆车它行驶的这个路径一些避撞的操作等等。我们的目标是要去最小化所有车辆行驶的这个总的行驶的这个时间。好，我们在模型中重点考虑这个避撞的这个问题，所以我们一共找到了34种避撞的这个可能会撞到的这个场景然后采取去相应的这个避撞的这个措施那么我们相应的这个假设条件比如说这是一些非常这个通用的，大家在这个 vehicle routing 问题中经常会用到的一些假设我们就不再这个赘述。那么我们的目标函数是最小化所有车辆的行驶的时间，我们有车辆和时间的约束，有通行规则的约束，我们还有这个避撞的这些约束等等。同时为了去增强这个模型的这个也就是比如说我们这个 C++ 等等这些软件求解的效果那么我们这个提出了2种这个不等式那么去规定这个车辆行驶的最短的这个路径的这个就是它的这个区间和它的这个时间最短的时间。那么这是我们的数学模型大家看起来可能会有点复杂这也是我们本文的主要的贡献之一。好，那么我们提出了一种改进的 A 型算法去解决整个的这个问题解决这个路径的这个调度问题。改进实际上也就是主要要考虑这个避撞的问题，因为这个一辆车它的这个路径会经过很多的路口，于是呢我们就以每个路口为单位，把这个一辆车的经过多个路口的一条路径打成这个，把它拆成多条这个路径，然后再以每一个路口为基准去综合所有经过这个路口的路径再重新去组成一个 group。 那么这样就找出在这个路口可能会有一些碰撞的这个情况，我们再去解决这个路口碰撞的这个问题大概就是这个 idea。然后基于这个 idea， 我们提出了一些新的这个 parameters 和这个路径改进的一些 idea 主要体现在这个我们对于这个评估函数的这个改进上这是我们改进 A 型算法主要的一些流程那么我们这个进行这个算力的这个对比我们主要是有我们的算力准备了3种一种就是我们只考虑1个周期也就是比如说1分钟那么这个区间我如何去调度。第二种情况就是我考虑2个周期也就是前1分钟和后1分钟，那么这实际上它就有这个时区之类的这种交互这个 case 如何去比较。再一个就是我们比较这个全局调度和局部调度，也就是当前这种模式它的这个优劣。我们进行了几组主要的这个比较一个是比较我们的模型有这个有不等式有效不等式和没有的，也就是这个加 cast 的这种情况和没加 cast 的情况。第二种就是我们的模型加 cast 和改进 A 型算法之间的这个结果。第三种就是改进 A 型算法和这个传统的 A 型算法的结果。第四种就是我们有跨区域，也就是刚才我们讲的这个跨子区域的这种情况 ，A 型算法求解的这个效果如何？还有就是全局和局部的这个对比。那么这是我们数据生成的这个过程对于这个有效不等式的效果它可以明显的去提升模型求解的这个速度那么这个对于改进 A 型算法和这个 C+ 去求解模型的这个结果我们可以看得到 C+ 可以求解21个问题的最优解，那么改进 A 型算法可以求得其中20个问题的最优解。 求不到最优解的有9个下界，那么改进 A 型算法也可以去 match 到9个下界，说明这个解它就是这个最优解啊。那么这个最关键的这个效果就是改进 A 型算法这个时间非常短啊，在0.005秒就可以求解。那么这个 gap 大概在1%以内，说明这个改进 A 型算法的这个效果比较好啊。那么这个下界的质量也还是不错的。那么这个改进 A 型算法，相对于这个传统的 A 型算法，可以明显的去提升这个求解的这个效率啊。然后呢，可以去改进这个车辆在交叉路口的这个等待的这个时间等等。那么对于跨区域的这种情况的话也就是我一辆车我行驶要穿过多个区域，那么区域之间的这个数据的这个交互，还有这个求解整个过程。那么这个改进 A 型算法它也可以求得比较好的结果时间也非常短，而且呢这个整个的这个跨区域和这个跨区域车辆多和不多这种情况，它求得的这个结果都是比较接近的，证明它有比较好的这个稳定性。那么我们对比整个的全局调度和局部调度的这个 case 我们以北京市的这个高峰期的交通流量这个为基准，北京市一天高峰期的这个交通的流量可能会在300万台左右这个样子所以说也就是大概是每分钟大概有2000台车进入到这个网络中，所以我们就比照这个规模，我们这个生成了一些相应规模的这个数据我们从500辆车一直到这个4000台车，我们在一个20×20的这么一个网络中去进行这个比较。那么我们的比较的结果是发现全局调度的这么一套机制可以明显的去减少整个交通网络的这么一个这个不均衡性对于它的这个均值它的最大最小值它的这个方差等等都有非常明显的改善。同时这个全局调度的这个模式可以明显的改善中心城区中心道路也就是繁忙道路它的这个工作的这个也就是交通的这个负荷。那么对于这个自动驾驶车辆和非自动驾驶车辆这个混合的这么一种模式，也就是自动驾驶车辆占比25%一直到100%。那么这个 case 的话，那么这个也改进 A 型算法也可以求得比较好的这么一些结果好，这个是我们整个的这个结果跟大家汇报。那么我们目前也有很多的这个工作因为刚刚开始也考虑的也有一些这个可能不周全的地方比如说我们考虑的是固定的这个时间周期未来随着这个情况是不是时间周期可以不固定我们还考虑在交叉路口我们有交通流量的控制，那么未来要更趋于这个实际的这个情况应该是怎么去做未来我们目前考虑的是分区的控制随着我们的这个算力的这个提升是不是可以不做这个分区的控制等等等等这些情况都可以在未来去考虑好吧那我的这个今天的汇报就到这里谢谢大家谢谢主持人。
感谢李老师的精彩报告，然后看咱们各位老师和同学是否有问题，可以跟李老师交流。
李老师，感谢您的精彩报告。我没有调到那个举手的那个图标，所以我要直接问了。
你好。
就是您那个微信算法在我们这边也用到挺多的，就是我想您这个改进的A型算法主要是从哪些角度去改进，以及有没有利用了您这个路网，就是说规规整整的这个特性去着手改进。
因为
第一个问题
好，
第二个问题就是说，您刚刚说可能有自动驾驶之后呢，就可能不需要有红绿灯了。那么那些行人或者骑自行车的人，他们怎么去参与互动呢？就2个问题。谢谢李老师。
这个李老师您提的这两个问题非常好，尤其是后一个问题，这也是我们目前这个感觉这个 limitations 里面有一个问题，就是我们目前这个只考虑了车和网络车和车之间的这个交互，目前这个车和人还有这个相应的这个基础设施之间的这个交互确实是考虑的比较少， 其实整个道路是公共交通的这个道路的这个网络，那么行人包括我们的这个自行车等等也要享有相应的这个通行权利啊，所以说这一块的话，我觉得未来是要深入去考虑去做的这么一块事情目前我们只是去比照这个我们已经有的一些场景，比如说在智能仓库中，它是没有行人的这个车辆应该怎么去调度实际上这个问题对我们来讲，它也起源于这个也就是智能仓库的这么一个 case， 实际上它是延伸到这个全局城市自动驾驶的这么一个交通网络所以这是我们的这个考虑对于这个改进的 A 型算法这一块的话呢因为这个问题它比较特殊一点的就是它是这种三格式的刚才跟您讲的那个问题非常像这个里面这个路径它最大的一个难点就是避撞的问题所以这也是我们在探索中的一个难点问题，所以我们也当时也想了很多的这个办法就刚才包括我们刚才说的这个你这个一条路径要经过多个路口每个路口它就有可能有路径的这个交叉，它就有可能有避撞的有这个碰撞的问题实际上这个跟我们这个自动仓库也就是这个智能仓库里面的这个避撞问题也非常非常类似，所以我们也采取了这个类似的这个办法，就是重新去组合，就是我把一个路口这个可能经过这个路口的路径都把它这个重新的这个找出来，重新组合，我再一个一个去比对，去找出在这个路口中可能碰到的这个碰撞的这个情况，那么我再采取比如说延迟出发或者是这个避让等等这种方式去规划这个路径具体的话呢这个到时候你有兴趣我们这个详细的去交流好吧
谢谢李老师
谢谢李老师
再看看其他各位老师同学
李老师你好我那个是香港理工大学王坤
老师你好
那个我想问一下对我觉得您的报告非常有意思也非常好非常前沿，我想问一下就是在这个避撞的问题里面的话我们用 A 型算法先比如说每一辆车先给它找到一个最短路径，然后把这些有可能碰撞在一些交叉路口碰撞的这些路径呢再把它拿出来，然后咱们再去做避障分析。那这个刚才您提到这个解呢其实还是很快的对吧，这个改进之后我看算的速度非常快但是就是说如果像比如说您刚才最后提的像北京这个 case， 这个您的计算速度有没有那个数据？另外就是像现在这种比如说用 reinforcement learning， 就是说我们用这个agent， 就是当然你比如说我们也先用 A 星先把这些可能碰撞的 case 找出来，但是咱们是不是有没有一些比如说用一些 AI 结合的，甚至把 reinforcement learning 和 AI 相结合的一些方式甚至像这种 large language model 我可能去把一些 policy function reinforcement learning policy function 这些方面的拓展，我不知道您有没有什么那个 insight， 当然我对这方面不是特别懂，但是看了一些相关的研究，就这些它可能在运算速度上会不会更快，或者是这个跟您现在的方法对比大概的这个 performance 是怎么样谢谢您。
好，谢谢您的这个问题实际上就都点到了非常重要的未来的要研究的一些东西实际上这篇文章我们当时写这篇文章的时候比较早也是2-3年以前我们就有了这个 idea， 就把这个工作做了很多，后来我们写成 paper 投到这边也录用了。实际上这篇文章因为我们想当时比较早的话呢，我们就先以提出这个全局的这种模式和把这个整个问题的模型建出来为主。实际上您看到我们这个算法是非常简单的前几年我们还这个在我们跟同学们在一起讨论这个问题的时候也讲后期我们可以采取一些更复杂的一些这个算法。实际上目前我们这个 paper 它的这个重点可能这个算法这一块确实是不是我们目前这篇 paper 它主要的这个重点之一所以我们首先是要提出这个概念说看这个概念大家这个能不能接受特别是我们的这个政府部门这一块未来是不是打算这么做的因为我们是觉得 目前的技术是已经是可以这么去做了，而且有一些成功的 case， 而且我们主要是去论证，在这种模式下它是有很大的好处的，它的整个路网的通信效率、安全性都会有大幅的提升我是想我们这个第一篇文章我们是要达到这个目的您说的这个后面讲的这个 AI 这个强化学习等等这些，包括一些这个 policy我觉得都可以把它加进去，都可以去研究这个问题。这也是我们希望说，我们提出了这个 idea， 我们希望这个如果大家觉得感兴趣，未来政府部门觉得这个有用，我们一起去研究，去把这个问题把它做深做透了之后，未来我们就提供一些确实可行的这个方法，政府部门它可以直接去采纳，可以直接去用到它的这个系统里面去的。刚才至于您说的这个北京的这个 case， 我们是模仿它的这个交通流量的这个车辆的这个数量。那么这个网络的话，大家可以看到它是一个20×20的这么一个网络，可能它要比我们实际的这个网络这个规模可能没有实际那么大但是呢，这个也不影响刚才我们提出的这个分片区的概念，也就是根据我目前的算法的这个效率和软硬件的这个水平来看，如果我的这个算法我能够让20×20的工作起来达到我的这个时间要求，那我就20×20。如果未来我们的算法改进了，我们的软硬件改进了，变成50×50也可以当然大家知道这个问题就是你这个随便加一个维度，它的这个复杂度会急剧的这个增加所以我觉得这个也是一个非常值得去探索的问题。
谢谢李老师，您回答的我觉得特别好
谢谢。
idea 非常重要，全局控制，因为现在技术确实基本上是可以去 support 这个想法的。
是啊。
好，谢谢李老师。
好，谢谢。
挑战的问题就是您刚刚提到的，就是全局上去做一些决策。就我在想，未来因为咱们从优化角度来讲，一方面，我们这个优化问题，我们需要追求它一些理论上的一些最优。那么我们在实际当中，是不是会更讲究它的时效性的一些要求？那在我们整个设计方法的时候，我们是不是会有一些取舍？就这个可能是比较关心的一点。
是的，这个黄老师，您这个问题也是我们有时候会考虑的一个问题，就是说我们这个理论上做这个研究的这个结果就是说我是更加的喜欢从这个实际应用的角度去考虑，就是说我们的理论研究到底如何服务于这个企业的这个实际。刚才您这个介绍的时候，也介绍，就是我会经常跟一些企业去交流特别是比如说像我们这个，它可能未来就要为政府去服务。那么政府服务的时候，比如说我这个车辆目前是局部调度的模式，它有很多的问题。我采取全局调度模式以后，哪怕我的这个算法的效率目前可能离最优解可能是60%、70%的这个距离，在我们理论上来讲就不是很好，但是它可以改变一种模式，它就可以取得很好的这个效果所以说像我们实际中像这个美团的这个算法像这个滴滴的这个算法像这个我们整个的这个路径等等这些算法，其实我个人认为，也许我们去研究它的这个算法，它隔最优解还有一段距离，但它实际中用得很好，它有非常好的这个商业的和实际的应用的价值。所以我觉得我的想法就是第一步，咱们用这个文章先这个把 idea 抛出来之后，政府部门觉得可以先如果可以先把这个平台先开始建起来嘛，是吧？好不好用再说，我们先解决有没有的问题，是吧？
对，非常感谢李老师的那个好，看看咱们还有没有其他问题，各位老师同学。行，那如果没有，再次感谢李老师的精彩报告，然后谢谢李老师。
谢谢主持人。
好嘞，行，那咱们今天的整个的论坛报告就已经结束了。咱们整个论坛覆盖了3个非常有意思的话题，包括从前面的电动公交车，高老师电动公交车的一些调度包括和micro mobility 的一些联动到咱们后面的廖老师的一个整个的人的出行链条或者是路径优化的一些相关研究。到咱们李老师的面向于未来的无人驾驶车辆的城市智能调度，所以整个论坛的覆盖面还是挺广的。然后反正咱们时间也刚刚好，今天的报告差不多到此结束。然后董老师，您看咱们是直接结束吗？ 那行，那好，那就谢谢各位老师和同学参与本次论坛，本次论坛到此结束。